Hello, and welcome back to Networks Explained Simply. This is video number 4 in our Network Fundamentals series. Click here to check out the rest of our playlist. In today's video, we'll be looking at special IP addresses and network address translation. Let's start off with a typical network, similar to those we saw in our last video. Here we have a network which ranges from 192.168.100.0 through 192.168.100.255, and which uses a subnet mask of 255.255.255.0 or /24. As we learned in our last video, this subnet mask tells us that there are 256 unique IP addresses on this network. Something we didn't discuss is that on every network, some IP addresses are reserved for special purposes, and these special IP addresses cannot be assigned to devices. The network address is one of these, and it's used for referring to the network as a whole. The network address is always the first numerical IP address on the network. And for many networks, including classes A, B, and C, the network address ends in .0. The network address makes it easier for us to talk about networks because we can express the entirety of a network's range in one brief notation. So instead of providing all of these details, now we can simply refer to this network as 192.168.100.0/24. It's important to note that the network address will not always be .0, and that not every .0 address is the network address for its network. Some networks will have a network address other than .0 because .0 simply isn't included in the network's range. In our example on the left, 192.168.100.128 is our network address because numerically it's the first IP address on that network. Some networks will have more than one .0 IP address, but only the first can be the network address. This means that sometimes there are .0 IP addresses which devices can actually use. In our example on the right, this network includes the IP address 10.0.1.0. But that IP address is not the network address for this network because it is not the first address in the network's range. So on this network, the IP address 10.0.1.0 is not special, and it can be used by devices just like any other address. Another reservation that exists on every network is for something called the broadcast address. The broadcast address provides a mechanism for sending information to every device on an entire network, which is a function that some applications depend on. Numerically, the broadcast address is always the last IP address in the network's range. In our example network, our broadcast address would be 192.168.100.255 because .255 is the last IP address in the network's range. With this list of examples, we can see that the number of usable IP addresses is always 2 less than the total number of IP addresses for each network size. And that's because of the required reservations for the network address and the broadcast address. Note that for these examples, we've kept the network addresses identical, and that the only difference from one row to another is the subnet mask. Finally, these columns show us the ranges of IP addresses which will be usable for devices in each network size. Here's a table showing every possible subnet mask, along with the number of usable IP addresses which each mask makes available. Feel free to screenshot this table for future reference. Before we close the topic of reserved IP addresses, it's worth mentioning a common misconception. There is no standardized reservation for routers on IP networks. It is very common to see routers which use a .1 IP address, or the first IP available after the network address, but this is not a standard. A network's router can use any IP address that's within the network's range. Now that we understand the universal reservations for network and broadcast addresses, let's quickly review the history of IP version 4 to prepare for our next topic. Introduced in the early 1980s, Internet Protocol version 4 allowed for about 4 billion unique IP addresses. At that time, the average home or business didn't have an internet connection, so access was mostly limited to academia, government, and military institutions. For the internet of the early 1980s, 4 billion unique IP addresses seemed more than sufficient for global needs. But by the end of that decade, internet service providers in the United States began offering internet access directly to homes and businesses. Soon after, many cable television and telephone providers saw opportunities with their existing infrastructure and became internet service providers themselves. This meant that for millions of homes and businesses in the United States, direct internet access became an available option almost overnight. This trend continued in other countries as well, and with this rapid expansion came an acceleration in the global consumption of IP addresses. An additional factor increasing address consumption was that, especially in schools and businesses, it was common to have multiple internet-connected computers in a single location. Since each computer needs a unique IP address, this meant that a single school or office building could consume hundreds of IP addresses. By the early 1990s, it was already clear that the accelerating global consumption of IP addresses was unsustainable and that something would need to change. So after much consideration, industry leaders decided on strategies for both the short term and the long term. In the long term, it was agreed that the best plan was to replace IP version 4 entirely with a new version of the Internet Protocol. With a new Internet Protocol, industry leaders would be able to change the number scheme of IP addresses in order to create a much higher number of unique addresses. Replacing the entire standard would also allow them to revise other details and optimize the Internet Protocol for the world's evolving needs. But this option had one major downside. Replacing the Internet Protocol meant that computers and networks using the new version would not be able to communicate with computers and networks using the old version. And with the Internet becoming ever more decentralized, coordinating a single global cutover to a new version was simply no longer realistic. So, introducing and adopting a new version of the Internet Protocol was likely the right decision, but it would take time to implement, and it would likely not be ready before the current pool of addresses would be depleted. So, in the short term, while a new Internet Protocol version was developed and tested, industry leaders looked for ways to slow down the consumption of IP addresses. They saw that the trend toward multiple connected computers per location was having an exponential impact on the problem, and that this trend was only likely to increase with time. If there was a way for multiple computers in a single location to somehow share an IP address, it would dramatically decrease the demand, but IP version 4 didn't offer any way to do that. So to make this possible, in 1994, a new private networking feature was introduced for IP version 4. This new feature would allow multiple computers in a location to share one public IP address by creating a separate network at the customer's location on which the computers used private IP addresses. These private IP addresses could then be used repeatedly around the world because they would never be seen on the public internet. Creating a separate private network at each internet customer's location meant that a computer's IP address only needed to be unique locally, not globally. In order for private networking to work with IP version 4, it was necessary to have specially designated IP addresses that would be off limits on the public internet. This meant that some existing ranges of IP addresses would need to be reallocated as private. and these specially designated IP ranges could never be used on the public internet, so internet service providers could not be allowed to control them. Here are the three primary ranges of IP addresses which are designated for use on private networks. Perhaps the most commonly used private network range is 192.168.0.0/16. The entire range of 192.168.0.0 through 192.168.255.255 is designated as private. This range is popular due to its simplicity, but the other ranges are also widely used, and there are no functional differences between them aside from the subnet masks that are available. In addition to these, here are some other specially designated IP ranges which have more specific purposes. A detailed discussion on each of these is outside the scope of this video, and this list is not complete, but it's helpful to know that there are other ranges of IP addresses which are reserved for various reasons. Now at this point, you might be thinking, private networking sounds like a good idea, but didn't we just say that private IP addresses can't communicate with the internet? Isn't that a problem? How do computers and devices on private networks use the internet? Well, as we learned back in our first fundamentals video, the primary function of a router is to connect with two or more networks and facilitate communication between them. But when a computer on a private network wants to communicate with the public internet, we will have a problem because, just like a letter you might send in the mail, every piece of information that we send on a network is marked with its source address and destination address. Since all routers know that private IPs are not allowed to communicate on the internet, any data that we try to send to the internet like this is going to be dropped or ignored by the very first router that it hits. In order to work around this problem, another new feature was introduced along with private networking, and that feature was called network address translation. To understand how network address translation works, let's consider this example, where a computer on a private network wants to browse to a website on the internet. First, the web browser application on the computer generates a web request, which asks for a copy of the website's files so that the browser can reconstruct the website locally and display it for the user. This request will be marked with a source address, which is the computer's private IP, and a destination address, which is the public IP for the website. When the computer sends this request to the local router, the router will immediately identify that this request is bound for the internet, but bears a source address that is not allowed to communicate with the internet. In order to work around this, the router uses network address translation to do two things. First, the router alters the source IP address on the request, changing it from the private IP of the computer inside the network to the public IP that the local building's internet connection uses. Typically, this public IP address lives on the router, and it's used by the router's internet or WAN port. Second, as it sends the altered request on its way, the router makes a note in its translation table so it can remember the alteration that it made. In order to do this, the router uses something called a source port number. We'll cover network ports in detail in a future video, but for now, it's enough to know that the sending computer randomly selects a number, which we call the source port, and that the request is permanently marked with that random number. The source port number does not change, and the router will remember the source port number that was used on the outbound request. When the web server receives this request, it will generate a reply. The destination for the reply will come directly from the source of the original request, and it will also reference the source port number in its reply as a destination port number. When the web server's reply makes its way back to our local router, the router will use network address translation again. Consulting its own translation table, it will remember that port 42712 was used as the source port on the original request, and that the request came from 192.168.100.105. Based on that information, the router will then alter the destination address again, this time altering it back to the internal private IP address for our computer. By using network address translation in this way, routers can enable communication between private networks and the public internet while maintaining the separation between private and public IP addresses that IPv4 requires. Let's conclude with a final note about network address translation. When we describe an IP network as private, all we mean is that its IP range is within one of the designated private ranges of addresses. This does not imply anything about the privacy or security of our network, because network address translation is not a security feature. In order to keep intruders from accessing our private network without permission, we will need to use something called a firewall, which we'll cover in a future video. In our upcoming lessons, we'll be looking at IP address management, DNS, network topologies, and much more. We'll keep all of it simple and easy to digest, so stay tuned. If you enjoyed this video, please remember to like and comment, as this really helps to make our videos visible for others. Also, remember to subscribe so you don't miss any of our future videos. As always, thank you so much for watching. We'll see you again soon.